Okay, the purpose of this podcast is to look at so-called circular functions, which will involve a development of the sine and cosine functions using the so-called unit circle. Some of you will be familiar with SOH CAH TOA and right triangle-based trigonometry definitions, and we'll link that to two-dimensional space with something called the unit circle. And in the process, as we develop this circular function, we'll talk about the distinction between degrees and radians. So here you see three so-called unit circles. Unit comes from the fact that the radii in each case is 1. And of course, where the radius is 1 and the circumference of a circle is 2 pi r, the circumference being the actual distance around the circle, we end up getting that the circumference is 2 pi. Now the context for 2 pi is kind of interesting. If you think about this point here I'm referring to as a starting point and go around a circle, then the actual distance around the circle in each of these three cases would be so-called 2 pi radians, as it turns out, in length. Well, pi, we all know, is approximately 3.14, so twice 3.14 is approximately 6.28. If you think about the fact that that length right there, which is the radius, okay, so the radius of 1 is all around the circle here, if that represents a length of 1, if you were to pick that up and sort of start here and kind of in a banana-shaped sense wrap it around this circle, you would see that that length would go 6 times with about 0.28ish left over. So there's your 6.28 in terms of a numerical length. Now we're starting to see some kind of an angle here, namely 45 degrees, and something that involves radian measure. So pi over 4 relative to 60 degrees, we see pi over 3, and pi over 6 relative to 30 degrees. And we'll explore that in just a second. So there is this linkage between degree measure and, as it turns out, what will be radian measure, which has something to do with arc length, as it turns out. So what might that be? Well, we're back to the fact that we're on the unit circle. The radius is 1, and we established that the circumference is 2 pi. And we saw that that's approximately 6.28 units when we think about pi traditionally as 3.14 units. However, if you draw a linkage between this entity of 2 pi as a length around the circle and say, well, any circle is, of course, measure-wise 360 degrees to get all the way around that circle, suddenly we have a kind of a link between degree measure and what will be radian measure. Have that, and you get that classically that pi is 180 degrees. And that makes sense because if you go 180 degrees over here in terms of forming that straight angle, you've actually gone just half of that circumference, which of course would be just pi radian in length. If you have that, again, you're talking about pi over 2 correlating to 90. So there's your 90 degree angle right here. And that arc length of pi over 2 corresponds to an angle opening at 90 degrees. And you get the idea. So you go back to basically this conversion factor. Divided by 4, you're here. Divided both sides by 3, you're here. Divide both sides by 6, and you're here. So these interesting 30, 60, 90 angles are starting to fall out, as well as a 45, 45, 90. So if you think about those three angles that we just formed, namely 30 degrees, 45 degrees, and 60 degrees, and correspond to those points on the so-called unit circle, 3 points, we can start to see and take advantage of some symmetry factors. So you could take those 3 points, and if you cut the circle right there and fold it over, those 3 points would land right there. So you'd have something that looks like that. You could further cut the circle here and fold that down, and these 3 points and these 3 points will land here, 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 and over here respectively. So we're starting to get a sense of symmetry to go around this circle, and suddenly we're talking about, if we use this as our sort of zeroed out starting point, that we can talk about a quarter of a turn being pi over 2 for 90 degrees. Here's half of a turn, so you got pi corresponding to 180, and you get the idea as you go around. So let's explore that a little bit more specifically when it comes to this kind of so-called manner in which we can define a circular function as it's going to relate to angles going all the way around the circle. And we can, of course, cut, like I said, cut here and here and fold these down and talk about angles that are actually in these quadrants down here. So if you think about it, we've got relationships between quadrant 1, 2, 3, and 4, because we're in the Cartesian plane there, and angles that, in terms of quads 1 and 2, go all the way up to 180. And then as we go a little bit further, here's quads 3 and 4, giving us the angles that go from 180 to 360. And we start to see these further radian clarifications. So we'll get into that a bit more deeply now. So here we are back at the unit circle. If you think about traditionally something like that 30-degree angle, which would form, as it turns out, a 30, 60, 90 triangle, there's something to do with this pi over 6 arc length. So we're starting to draw a relationship between 30 degrees in degree measure and pi over 6 in radian measure. You might recall that your classic ratios from 30, 60, 90 are of course 1 root 3 to 2. So hiding in this information as we begin to say, well, how does this circular function, in terms of how we might begin to define the sine function as well as the cosine function, what does it actually look like, and why does it allow for this wave-like form of it? Well, here is the classic sine curve, whether you're familiar with it or not. This is your classic sort of interval here as it repeats. So we see that if you were to sort of say, well, let's start here at 0, and let's just track these y values as we actually go around this circle. Well, the y values start at 0, and then they go up to 1. Well, here they are starting at 0 and actually going up to 1, and that oneness occurs at pi over 2 or 90 degrees. And then the y values drop from 1 back down to 0. Here they are dropping from 1 back down to 0, and of course we've accomplished pi radians or 180 degrees. What do the y values do now? They keep going. They drop down to -1. Well, here they go from 0 down to -1 for the next quarter of a turn, and then from -1 back up to 0. And so that actual movement around the so-called unit circle accounts for the actual flow of this wave, which we call the classic sine curve. And you can see that that just keeps going in that direction, and we could also keep going in this direction. So, we started here and did a turn that was 2 pi. We could actually keep going for 4 pi, 6 pi, you get the idea, and that wave just keeps going. And in fact, we can start here and we can work in what's called a negative direction and start to talk about negative angles. So let's go a little bit further and consider, why does the actual cosine graph look the way it does that you see here in red? Well, if you go back to the beginnings here and say, well, if we actually think about the x values now, which is technically how the cosine of theta is defined, this can be a little bit confusing to you. We'll maybe address that in just a second. But the x values, as you're starting at this 0 place, the x value is actually over at 1, 0, and that's why at 0 we started 1. And then as you do that quarter turn, what do the x values do? They actually work back to x of 0, and here they are going back to x of 0. And then they go further to -1. Here they are going further down to this -1. And then they start to work back as you go from there to there. Those x values go back to 0. Here they're going back to 0. And as you finish up this final turn, they go from 0 back to 1. That's why they finish high up here at 1 again. And keep in mind that this axis is, these are real numbers. So we're seeing roughly 3.14 here, and we're seeing roughly 6.28. And they correspond, of course, to 180 and 360 respectively. So, okay, a lot going on here. Something for you to consider now. So I've thrown a lot at you by way of these so-called circular functions. If you go back to traditional SOH CAH TOA, 30, 60, 90, and 45, 45, 90, you can see the beginnings here. This would actually be technically quadrant 1 in terms of the Cartesian plane. What is the sine of 30 degrees? Well, it's, opposite over hypotenuse. So the sine of 30 is 1/2. What is the cosine what is the sine of 60 degrees? Well, it's opposite over hypotenuse, root 3 over 2. you get the idea. So you can actually use these traditional SOH-CAH-TOA ratios to begin to get a sense of sine and cosine. And so we haven't even talked about 45, 45, 90, but that information is hiding in here as well as you go around the actual circle. So, what is the cosine, for example, of 45 degrees? Well, it's adjacent over hypotenuse. It's 1 over root 2, which rationalizes to root 2 over 2. So here, what I've begun for you is the values for the so-called special cases, right? These angles you see here. Well, if you go beyond the first quadrant and go into quads 2, 3, and 4, to traditionally go around the circle in a circular function sense, whether you do it for the sine curve to get the rest of these values, or you do it for the red cosine curve to get all of these values, I would hit the pause button if I were you and play around with your calculators a little bit, play around with the concepts, and see if you can actually fill in the rest of the table, because you're going to find a displacement of all of these values, and all that's going to happen is their signs are going to change in terms of plus or minus values in terms of the symmetries of those circles we talked about all the way at the very beginning. So hit pause and good luck. How'd you make out? There are the final values. As promised, all of these values just get displaced because of the nature of all of the symmetries going around the so-called unit circle as we explore the sine and cosine functions from the perspective of the so-called circular function. So I hope that was useful for you as a quick overview, trying to draw a relationship between degrees and radians and your traditional SOH CAH TOA sense of sine and cosine relative to the 30, 60, 90, 45, 45, 90, and to see how those special triangles just get displaced into a variety of quadrants to account for the rest of these relationships. Okay? Good job. Thank you. Bye.